Okay, so now that we've done some direct proofs, this time we start looking at another common proof, which is the proof by contradiction. Now, a proof by contradiction is where, given our statement P, then trying to prove Q there, right? A proof by contradiction is where we assume the opposite of our outcome. In that case, P 2, this is the symbol used to not Q. So we assume the opposite there. And what this is basically means that we assume that what we're trying to prove, we assume that the opposite is true, right? If we assume that the opposite of this is true, then through our proofs we will lead to a logical conclusion that will show us that, okay, what we assumed to be true is actually false. In that case, if the opposite is false, mean automatically the original statement itself must be true. Now, one common way of proving this, one common proof that we use contradiction for is the proof of square root of 2, right? So prove that square root of 2 is an irrational number. So in this case, we've been given square root of 2 and want to prove that, okay, it is an irrational number. In this case, it being an irrational number is our Q. So how do we do this? Well, we assume the opposite, right? So we're going to say, okay, given that we know that, okay, we know that we have square root of 2, we're going to assume that square root of 2 is rational, right? So that's how we start off with our proof. So we're going to start off with 7, then we're going to say sort of my proof there. So we're going to say proof, then under that proof we say assume, we're going to assume square root of 2 is rational, like that there, right? We'll assume square root is rational, and for a rational number it can be expressed in the form a over b, where a and b are in their lowest forms, right? And a and b are members of our set of integers, like so, right? So a and b should not have any common factors, they should be in their lowest forms, and they should be integers. So let's start with our actual proof now. So we begin by saying, just split my board, like so we begin by saying square root of 2 is equal to a over b, because in this case we've assumed that square root of 2 is rational, right? Then we square both sides, so we have 2 is equal to a squared over b squared, right? Which then gives us 2b squared is equal to a squared, right? Now this shows that a is even, right? Because remember, we said that any even number, so if we have an even number, if we have a number t, it's even if it can be expressed in the form 2n, right? So this shows that a is even, right? So a squared is even, so a squared is even. Now if a squared is even, this also implies that a is also even. Now we never did a proof for this, but you can actually do this as some exercise for yourself. So you can try proving the fact that if a is even, then a squared is also even. So I'll add that, I'll give you that question. So now, since we know that a is even, right, a can be written in the form a is equal to 2r, where r is a member of, again, our set of integers. In that case, what we have is 2b squared is equal to 2r squared, like so. Then we have 2b squared being equal to 4r squared. Now if we have that, if we make b squared subject to the formula, we have b squared is equal to 2r squared. This also shows us again that, okay, b squared is even. Now since we know that, so if b squared is even, then b is even, right? B is also even. Now remember our initial condition that we had set up over here, right? Over here we said that these two should be in their lowest forms and should not have any common factors. But if both of these two are even, it means that, so therefore, let me say, this implies a over b is not in its lowest. form. Reason being, these two have a common factor. So because 2 is a common factor, right? And if that's not the case, right, if our initial assumption is wrong, because we assume to say, okay, this is rational, it can be expressed in the form a over b, right? Can be expressed in this form. But through our proof here, we've said that, okay, we can't prove it like this, which automatically means that our initial statement is right, meaning that we're right in saying that square root of 2 is irrational, right? So just to walk through that again, first thing we do, we assume the opposite, right? So we assume that square root of 2 is rational, meaning it can be expressed as a over b, where a and b are in their lowest terms, meaning they have no common factors. Then from there, everything goes on like a normal direct proofs, the direct proofs that we've been doing. So the only difference is what we have here, and of course what our final conclusion will be like. So over here is basically like a normal direct proof. So yeah, how we've been proving directly. But then once we prove that, okay, a squared is even and b squared is even, this leads us to a contradiction because the common factor there will be 2. But our assumption was that these things are in their lowest terms. So meaning square root of 2 is irrational. Okay, now let's move on to another question. Let's give you a chance to copy that down. Now we move on to another question, which is a similar thing. So it's question 8. So question 8 like that. So question 8 is, prove that 1 plus root 3 plus 3 root 2 is irrational. So how are we going to do this one, right? How are we going to solve this proof? Well, first of all, we assume 1 plus 3 root 2 is rational, right? We assume that this is rational, right? So if this is rational, then we can say, so instead of our proof, we can say 1 plus 3 root 2 is equal to a over b. Now, in having this, so where a, b are members of Z and have no common factor, meaning they are in their lowest term, right? So we're going to prove this now as a direct proof. So we're going to say 3 root 2 is equal to a over b minus 1, right? If we simplify this, we have 3 root 2 is equal to a minus b over b, right? If we divide both sides by 3, we have square root of 2 is equal to a minus b over 3b. Now, what do we have here? In the previous proof, we said that, okay, this is irrational, right? We know that root 2 is irrational. We already know that this is irrational from the previous proof over here, right? We already know that this is irrational. But what we have over here, right, what we've come to here is saying that, okay, no, you know what? Square root of 2 is rational, which we know to be false from our previous proof. Hence, right? Hence, this is a contradiction. Implying 1 plus 3 root 2 is irrational, right? So again, to walk back what we did, so we say we assume it's rational, and if it's rational, it can be expressed as a fraction of two integers, in this case a and b, where these are in their lowest terms. But then through this proof, it led us to the conclusion that the square root of 2 is rational, because we have square root of 2 being equal to a minus b over 3b, which is a rational number. But you know that this is false, because from our previous proof we said that, okay, this guy right here, square root of 2 is irrational. So meaning this conclusion is false. And if the conclusion is false, it means our initial assumption is false, meaning that our original statement is true. Hence we've proven that this one is also irrational. So this is how you do a proof by contradiction. So yeah, I hope you enjoyed this session. We'll move on to proofs by introduction next.